So in this video, I'm going to go ahead and look at a more complicated problem that involves three vectors. So pretty much after this, hopefully you can add as many vectors as I give to you. So let's say somebody was going off on a hike and they got lost and didn't return, and we had the path that they had planned on following, and we wanted to determine where should we, concentrate our search. So let's say they first said that they were going to go 5 kilometers, 35 degrees north of east, and then 6 kilometers east, and then 4 kilometers, 20 degrees south of east. And so we really want to know how far away from the original location and in what direction do we have to begin. So let's go ahead and start by drawing our vectors, and then we'll perform the component method in order to determine where they actually are. So I'm first going to place a little origin here at the beginning, and I know that it's 5 kilometers and it's 35 degrees north of east. So if I use my protractor, 35 degrees north of east is over here, so that's going to be roughly right there. And I'm going to try to draw these pretty to scale so you can tell. So let's go ahead and just draw my first vector. So let's say that's roughly 5 kilometers there. So I've got 5 kilometers, and that's at an angle of 35 degrees. All right. Then the second vector is directly east, so that makes my life a little bit easier. I'm going to go straight in this direction, and we're going to go 6 kilometers. So again, I'm going to draw my second vector at the tip of my previous vector. And so I essentially just put a new little coordinate system there, and so I know it's going to be straight east. I'll try and make it a little bit longer than the last one. A little bit longer. And so that's 6 kilometers. And then my third vector is going to be 4 kilometers, 20 degrees south of east. So if I draw a new little coordinate system here, and it's going to be south of east, so that would be below the east axis. So I'm actually going to turn my protractor over like this and sort of mark that 20 degrees is about right here. And so if I do, well, it's supposed to be 4 kilometers, so I'll make it a little bit shorter than the first one, roughly that. And this is 20 degrees there. All right, so my resultant should be easy to tell that it's from here to here, right? And if I were to draw it in, let me just go ahead and draw it in with a pen so we can see where it is. And we can kind of make a guess of what it is, what size it is. All right, so remember, from the tail of the first to the tip of the last, and it's an arrow. And so just by eyeballing it, I'm going to make an estimate and say that's roughly, I don't know, maybe twice as long as this one. And again, it's not perfectly to scale, so let's just say it's about maybe 13 kilometers. It looks a little bigger than twice. 13 kilometers. And if I were to guess an angle, maybe I would guess at 10 degrees north of east, right? So let me go ahead and then use my component method in order to determine what the actual resultant vector is. So we're going to take the x and y components of each of our vectors. So let's start with the first one. Got an x here to the right and a y up, right? So this would be vector 1x, and this would be vector 1y. So in order to calculate that, I'm going to take the vector 1x is equal to, and we'll say the cosine of 35, and then I would multiply by hypotenuse in order to get the length. So let's do that. So the cosine of 35 times 5 gives me 4.1 kilometers, and it is to the right, so I'm going to make it positive. And then let's do my vector 1y, which would be the sine of 35 times 5. So the sine of 35 times 5, and I get 2.87. So 2.87, and just by looking I see that my arrow goes up, so it is positive, right? Now, the next one is easy, right? Because this component has no y component and it only has an x component. So vector 2x would be straight to the right, and I'll just write over here so we'll get them all in line at 6 kilometers. And vector 2y is actually 0 kilometers. Right? And then we're going to do our last vector, which is this red vector over here. And I try to make it so that my sines and my cosines are always the same component. So in this case, it's set up that way, but if for some reason I wanted to use this angle, I could. Sometimes I'll change the angle that I'm using just to make sure I'm always using the same trig function for my x and the same trig function for my y. It just helps me to make sure I'm doing the right thing. So let's go ahead and draw this components to the right, and then the y components down. So notice that my y component is actually going to be negative because it points downwards. And my x component is positive because it points to the right. And this makes it so I don't have to figure out like where in the coordinate system. So remember when I draw my coordinate system here, I'd have to go all the way around here, and if I plugged it into my calculator, then it would come out negative. But I just want to use 20, and I want to look here and see that, well, the vector points down, so I know that it's negative. It makes it easier than trying to figure out what that 20 degrees actually is. So let's go ahead and find out the cosine. Sorry, my motion sensor lights went off. All right, so we're going to find the cosine to find this vector. So the cosine of 20 times the hypotenuse, which is 4. So cosine of 20 is 4. I get 3.76. Okay, and then the third one is the sine of 20 times 4, which gives me 1.34 or 1.37, and it's going to be negative 1.37 since that points down. All right, so I've got all of my components, and so the next step is to go ahead and add the components of each of the vectors, of each of the x's and the y's, and that will give me my resultant x. So my resultant x is going to be equal to the sum of these if I add them all together, and my resultant y will be equal to the sum of all these. And again, we can visually see that my x is going to be this plus this red one, if I were to bring it down, would give me my x component of my resultant vector. And the y component would be equal to this minus this, right? So it would be this is their y. And so I have my right triangle in order to do my Pythagorean theorem. So let's go ahead and figure out what that is. I get 4.1 plus 6 plus 3.76, and that's 13.86 kilometers in the x direction. And then in the y direction, I have 2.87 plus 0 plus a negative 1.37, and I get 1.5 kilometers. Right? So I have the two sides of my right triangle, and since this is kind of a messy here, let me just kind of transfer that over to another sheet, and we'll come back and look at this when I'm all done. So I have my y, or my x component, excuse me, which is 13.86, and I have my y component here, which was 1.5, and then this was my resultant vector that I'm trying to solve for. So I want to know the angle, and I want to know the length of that hypotenuse. So I'm going to use the Pythagorean theorem, so 13.86 squared plus 1.5 squared, and then take the square root. And I get 13.94 kilometers. And then the angle would be taking the opposite over the adjacent. So that's tangent, but we're going to do to the minus 1 of 1.5 over 13.86, and that will give me the angle theta. So it's about 6.2 degrees. Alright, so the answer to this problem is that I should search for the hiker 13.9 kilometers at an angle of 6.2 degrees north of east. And if I go ahead and take a look at my estimate here, I was pretty close, right? So 13 kilometers, 10 degrees north of east. Right? So the moral of the story is that it is a lot of sort of busy work to solve these vector components, but you use the same method over and over and over using this component method, and you should be able to determine the resultant vector for any number of vectors provided to you.